All right, welcome back. Here's the perfectly elastic collision, the second technique. The reason why I used C and D before is because I wanted to use A and B for the initial values. So first let's set up the definitions here. A is the initial velocity for the 5 kilogram mass, B is the initial velocity for the 8 kilogram mass, C is the final velocity for the 5 kilogram mass, and D is the final velocity for the 8 kilogram mass. So we're going to set it up, again, I'm going to do a derivation first just to see what the result is. Once we have the result, then we're going to just use the result. In future problems using this technique, you do not have to derive it every single time. So let's just set it up. I know that our momentum equation, so this is our change in momentum is 0, in other words, conservation momentum equation is that m1a plus m2b equals m1c plus m2d. So I have two masses for the one-dimensional collision. Again, it's a one-dimensional collision. Perfectly elastic. We'll throw in here. Probably should have done it on the other ones, but these are one-dimensional problems. Mass times the initial velocity, mass 1 times its initial velocity plus mass 2 times its initial velocity is equal to mass 1 times the final velocity plus mass 2 times its final velocity. All right, our kinetic energy, the fact that kinetic energy is conserved, gives us 1/2 m1a squared plus 1/2 m2b squared equals 1/2 m1c squared plus 1/2 m2d squared. This is just the kinetic energy, individual kinetic energies added together before is equal to the total afterwards. That's part of the perfectly elastic. The collision, again, collision tells us that momentum is conserved. Perfectly elastic tells us the kinetic energy is conserved. So, got to do a little manipulation. What I wanted to do is I want to get all the mass 1s on one side and mass 2s on the other. So what I'm going to do is I'm going to bring mass 1c over to the left and mass 2b over to the right. 1/2 mass 1c squared over to the left, 1/2 mass 2b squared over to the right. On the second equation, I'm also going to multiply everything by 2 just to get rid of the 1/2, or divide by 1/2, same as multiplying by 2. And so what I end up with here for this equation is m1a minus m1c equals m2d minus m2b. This equation right here, again, getting rid of all the 1/2s, is m1a squared minus m1c squared equals m2d squared minus m2b squared. There is simple algebra going on here, but based on some of the stuff I've seen students do, it's not as simple as some students do. We do need to factor. So what I'm going to do is I'm going to factor this equation right here. I factor m1 out, so that's m1 a squared minus c squared equals m2 d squared minus b squared. I can factor it one more time. I can factor this is the difference of perfect squares. So a squared plus a, let's do some different letters. M squared minus n squared is just m minus n times m plus n. This is algebra 1. If you've forgotten it, you can convince yourself by foiling. If we FOIL, we get m squared outer plus mn inner minus mn last minus n squared. Those terms cancel out. I'm left with m squared minus n squared. So this becomes m1 a minus c a plus c is equal to m2 d minus b d plus b. If we factor it one more time. The top equation we're going to factor also, and I'm going to do a different color here just to the typical stunning visual effects. So I'm going to take this one and I'm going to factor this one. So I have m1 a minus c equals, and surely I've got a better green. There's a better one. So I have m1 times a minus c, factoring m1 out over here, factoring m2 out, d minus b. So I have my two equations here, and I factor them down as cleanly as I can. The next step is I'm going to divide. And again, the math people tell me as long as I divide both sides by the same thing, they are absolutely fine with fine with doing it. So I'm going to divide the left sides and I'm going to divide the right sides. I cancel out common factors, so M1 cancels out, A minus C cancels out. On the right-hand side, mass 2 cancels out, D minus B cancels out. What I'm left with is A plus C is equal to D plus B. We've now taken both of these equations and simplified it down to something relatively simple here. Getting into more common form, A minus B equals D minus C. Putting it back in the original notation, because I think that'll make a little bit, I'm hoping it'll make a little bit more sense. We have A minus B, so this is V1 initial minus V2 initial equals V2 final minus V1 final. I guess over there I have different subscripts of 5 and 8 instead of 1 and 2, but hopefully you tracked it. I have two masses here. This right here is the difference in the velocities before the collision. This is the difference in the velocities after the collision. There is 1 minus 2 and then 2 minus 1. This on the left-hand side is called the relative speed of approach. So if you've got something that's cruising along at 5 meters per second and this one's cruising along at 10 meters per second, both of those relative to the ground. So if this is, pick different numbers. So this one's going, let's say 40 miles per hour. This one's going 60 miles per hour. The question is, how fast is this one going relative to this one? Because usually when we talk about speeds of car, we talk about it relative to the ground. Oh, apparently I've got another class coming up. Oh, nope, just a text message. All right, so it's cruising along like this, and so if this one's going at 40 and this one's going at 60, well, relative to this car, this one's going at 20 miles per hour. So it's just the difference in the velocity which tells us how fast the first object is approaching the second object. So in our example up here, the difference in the velocities, it's 3 minus negative 4. So from his point of view, it's traveling at 7 meters per second this way. This is the relative speed of recession. So this is sometimes written down, I was about to say simplified, not necessarily. This is relative speed of approach equals relative speed of recession. So if from 2's point of view, the second one's point of view, the first one's coming at it at 7 meters per second, after the collision, the first one, from the first one's point of view, the second one should be going away at 7 meters per second. We can solve that now. And again, I guess I don't have to wait for you to write it down because you can always pause it and write it down. So we go back to our equations. Again, we have negative 17 is equal to 5c plus 8d. And we also have 3 minus negative 4 is equal to d minus c. Those are the two equations we're working with. This is a whole lot simpler. The quadratic has already been taken care of. And so here we have c is equal to, actually we can solve for d, it might be easier. So this is 7 is equal to d minus c. And so d is equal to 7 plus c. I plug that into the first equation. I get negative 17 is equal to 5c plus 8 times 7 plus c. So negative 17 is equal to 5c plus 56 plus 8c, distributing. And again, going for the darker marker. So I have, subtracting that from both sides, minus 56. So that's negative 73 is equal to 13c. And so c is negative 73 thirteenths. Negative 5.6154 meters per second. It's exactly what we had before. And d should be 7 more than that based on this. If we had 7, try that again. We get 1.3846 meters per second. And that is the same solution as we had before. So the second technique, the nice advantage is you're not dealing with a quadratic. The disadvantage of it that I've seen in the past, well, you still have the disadvantage of making sure you know what the positive and negative direction is. But the disadvantage I've seen is people getting the things backwards down here. That it's A minus B is equal to D minus C. If you get one of those backwards, then the whole thing gets messed up. So that is something to keep take into account. The third technique, which we'll come up to next, that's the technique that I personally prefer, but it has its own pluses and minuses. And so I'm going to stop it here, check my text message, and then start up for technique number 3.